Assalamualaikum warahmatullahi ta'ala wabarakatuh and good afternoon. I'm Dr. Sababau from the Physics Section, Pusat Pengajian Pendidikan Jarak Jauh, University Science Malaysia. This is course JIF 318, Quantum Mechanics. Okay. This is at the bottom here is my email address. If you have any questions, then basically you can email me using that email address. Okay, before we begin, let us check our academic planner, because our lectures or our course will follow the academic planner quite strictly. Okay. So this course is basically shared with, I share it with Associate Professor So Kim Guan. Okay. Actually, Dr. So Kim Guan is the more or less course manager. The marks will be collected by him, and I'm just as a temporary lecturer. Okay, it's a 3-unit course, and the textbook or reference book used for this course is by Robert Scherer, Quantum Mechanics and Accessible Introduction. Okay, concerning other learning materials, okay, it is in the e-learning usm.my, or we call it e-portal, and you can go through the e-portal basically to look through at other learning materials. For this course, the contribution of marks, final exam will be 70%, assignment 10%, continuous examination will be 20%. Okay? And for the final exam, usually we have 5 to 6 questions for 3 hours. Assignment, you will have 2 assignments. The first assignment will be before the intensive course, that means in the first semester. The second assignment will be in the second semester. We have only 1 continuous examination. That means for the first semester. The topics covered in the first semester only. Okay. Included in the academic planner is the assignment question. For example, like shown there, assignment 1. Okay. The deadline for submitting this assignment is 13th November, but I think you can pass it up on 31st December, and I don't mind. The most important thing is the assignment should reach me before the end of the year. That means 31st December. And assignment 2 is also included in the academic planner. Please look through your academic planner and do the assignment questions. Okay. This is more or less the web page for the e-portal. Okay. When you open up the e-portal, you will see this at the moment. Okay. You can see that most of the material, webex recordings and the letters or whatever, are still in the previous year mode. That's why most of them are what you call it blocked, so that you cannot read it. Actually, this is for previous years materials, so might not be relevant to you. For example, like Rakaman, webex, and so on and so forth is from last year. This year might be little bit different. But I would like to attract your attention to the lecture materials. It is in the left top corner there. You can see e-kuliah. Actually, I had recorded some e-kuliah materials. That means recorded lecture that covers the chapter 1, chapter 2, chapter 3, chapter 4, chapter 5, chapter 6, according to the lecture, not according to any books, but according to the lecture materials. If you click on that, then it gives you some of the material inside that chapter. Okay, for your information, I will cover the first 3 chapters. That means from the introduction to the Schrödinger equation, while Dr. Saw will cover the other 3 chapters. Okay. So, for example, if you click on chapter 1, you can see this. Okay? If you click on chapter 1, you will see chapter 1, then you have this. Basically, the reel here shows that it is a recording of 1.1, preface, example, and so on and so forth. So in each chapter, you have several topics. For example, like in the first chapter, you have preface or introduction, black body radiation, CP, classical physics failure, black body radiation, Planck hypothesis, classical limits of Planck formula, photoelectric effect, Compton effect, wave particle duality, the wave nature of matter, and so on and so forth. Okay. The same thing, if you click chapter 2, then the topics to be covered in chapter 2 will be shown. The same thing with chapter 3, and so on. Okay. So anyway, some of the material are quite out of date because the recording was done a few years ago. You still sometimes have to supplement your knowledge by reading the recommended books. Okay. That material or lecture material is not only shown on the left top corner of the material, but also in the list of the e-portal, JIF. That means the main list of JIF. If you go down, you can see JIF 318 e-kuliah. And basically all the recordings are also there. So you can look through or watch the recording and learn from the recording. This is basically more or less 15 minutes recordings, so that you can spend your precious time, valuable time, looking at it when you are free. It is not long. Most of the recording are about plus minus 15 minutes. So if you have free time, 15 minutes, just watch the recordings, okay? And the recording basically covers the entire syllabus of this course. And apart from the recording itself, at the top of JIF 318 e-kuliah, you can see webex conference note. This is my notes when I present in webex conference like this, because we have more than 30 recordings, so and notes. I cannot afford to have all those in 1 hour session. So usually, for example, like here, this is the previous year's 12016, and I will use the same material. You can see that it is up to 6. That means we have 6 video session or webex session, and we basically collect all those topics into 6 video sessions. Okay, So you can have a look, click on it, and you have the notes which I base my webex conferences. Okay. So for this session, for this session, that's been the webex conference session 1, we'll concentrate on the preface, black body radiation, classical physics failure, black body radiation Planck hypothesis, and classical limits of Planck formula, photoelectric effect, Compton effect, wave particle duality, and the wave nature of matter and the Bohr atom. Okay, we will concentrate on this in the first session. So let us go to the lecture notes. Okay, and why we need to study quantum mechanics, because most of the advancement of science in these few decades are based on quantum mechanics. Okay, as you can see from the main slide here. Okay, it is a gateway to modern physics. Okay, gateway, that means before that we have studied classical mechanics, okay, all the classical physics and so on and so forth. But the in the past few decades, that means a few tens of years, the new discoveries in physics are mostly based on quantum mechanics. Okay, atomic physics, nuclear physics, particle physics, and condensed matter physics are all based on quantum mechanics. That's why we need to really study this. Okay, that's why modern physicists need to study quantum mechanics. That's the reason why we need to learn quantum mechanics. Okay. To a large extent, the story of 20th century physics, okay, is the story of quantum mechanics. So quantum mechanics plays very important role in new discoveries, new recent and modern discoveries. The problem is that quantum mechanics is quite troublesome because it involve mathematics. That's why in chapter 2 we'll discuss some mathematical formalisms which are commonly used in quantum mechanics. Okay. So the result of quantum mechanics frequently run counter to our own physical institution. It uses several areas of mathematics, so you need to more or less really master some mathematical formalism such as complex numbers, linear algebra, and calculus. Okay, and most of the discussion of quantum mechanics are inside your brain. That means we call it Gedanken experiment or brain experiment. So people play mathematics and they get this result. Then experimentalists, that means physicists who do experiment, will try to prove whether the result is right or not. For example, in classical physics, you are familiar with classical mechanics, electricity, magnetism, and thermodynamics. Classical physics means whatever we had studied previously in those topics such as mechanics, motion, electricity, magnetism, electrostatic, electromagnetism, and heat, and so on and so forth. And when we study modern physics, usually it grew out of quantum mechanics. That means we have to really understand quantum mechanics in order to study atomic physics, nuclear physics, particle physics, condensed matter physics. Condensed matter physics, which was previously is popularly known as solid state physics. Okay. So the mind map, more or less like this, classical physics, still relevant when you study classical mechanics, electromagnetism, thermodynamics. Quantum physics, Okay, we study modern physics. You need to know quantum physics. You start from quantum physics. Then quantum mechanics basically is to study all the details of the atoms, nuclear physics, particle physics, quantum matter physics. So we are not saying that when we study quantum mechanics, then classical physics is not right. We should discuss, or we should throw away classical physics. No, classical physics is also still relevant for everyday life. For example, like when you're talking about a car moving, a ball traveling in air, heat, and so on and so forth. They're still valid, but classical physics cannot explain what is happening inside atomic physics, nuclear physics, particle physics, condensed matter physics. Okay, you need another mechanics, which is quantum mechanics, to explain those physical characteristic or physical properties of material. In usually you can see here that it is in minute scale. That means in atomic scale or nuclear scale. That means very small mass of matter. Okay. The proposition of classical physics, the previous when we study previously about classical physics, the physical universe is deterministic. That means you can determine the position and momentum of a ball, for example, or a car, or a body, whatever body it is. Okay. Then we also studied that light consists of waves. When we study interference, diffraction in optics, so light consists of waves. We use wave properties. That's why you have to study that called waves and vibration. And for example, in electromagnetism, we study, for example, impedance and so on and so forth based on wave properties. Okay. While matter composed of particles, matter, whether a piece of cake or whatever, your table consists of particles, atomic particles. So it is deterministic. We can differentiate. Light consists of wave, matter composed of particles. Physical quantity such as energy, angular momentum, can be treated as continuous variable. This is normal. For example, if you are driving a car, you press your accelerator, then your car increases in speed gradually. That means continuously. Or while braking the car, your car slows down continuously until it stops. This in everyday life, in our experience. Okay. Then there exists an objective physical reality independent of any observer. That means whatever physical action going on in the whole world will not depend on any observer. That means whether you are observing it or you are looking away from it, the physical reality is there. Those are the proposition. That means the idea of classical physics as a whole. Okay. But quantum mechanics says they are not completely what? Not completely accurate. That's why some people find it that quantum mechanics seems to contradict classical physics. But you can see from the sentence here that quantum mechanics does not really say that classical physics is wrong. It is only that it's not completely accurate. Okay. The first proposition of quantum mechanics is that the physical universe is not deterministic. That means you cannot determine exactly where a particle is or what is its momentum at certain position, a certain time, exactly. You cannot determine exactly, precisely. Okay? So we have to assign probabilities. But at this location, the probability of a particle, for example, at this position is such and such percent. Okay? It never predicts exact results with certainty. Okay? Exact certainty. There is no exact and certainty in quantum mechanics. Later we'll discuss about this probability. Yeah? Both light and matter. Just now, light consists of waves, matter consists of particles. But quantum mechanics says light and matter exhibit particle and wave properties. That means both light and matter. Light means electromagnetic wave, which has no mass. It exhibits particle properties as well as wave properties. The same thing, or on the other way, matter, that means consists of particle with mass, exhibit particle, yes, they are particle, but also wave properties. That means light and matter now have particle and wave properties. Some physical quantities are quantized. Some physical quantities have discrete values. That means they are quantized at certain level of, for example, inside an atom. The orbital electron cannot have continuous energy. That means it cannot have any arbitrary energy. Any energy is like, it needs to have certain discrete energies. So that's why we have the K level, L level, M level, energy level, and so on and so forth. So that means in quantum physics, some physical quantities are quantized. That means they cannot have any arbitrary values. It appears that the fourth proposition is that it appears that observer always affects experiment. That means, if, for example, if you want to study a particle such as an atom or a molecule, you need to give some energy, for example, like light, in order to see it. But of course, you cannot see an atom. Or you use other methods such as electric field or magnetic field in order to observe what, like in electron microscope, okay? You need to have magnetic field and so on and so forth. When you apply that in order to observe it, the energy of the electric field or magnetic field or energy of light used will affect your experiment. It affects the particle. It gives energy to the particle. So the particle initially, maybe, let's say, a particle is at rest. When you shine a light on it, then it gains energy. Then it starts to move or vibrate and so on and so forth. Okay? So you can see that the proposition of classical physics and quantum mechanics is quite opposite of each other. So which one is correct? And why would anyone believe in those ideas? Basically, it works. This is the most important thing. The idea of quantum mechanics works in experiments. However, you must see that this quantum mechanics is in a domain quite different from our normal everyday life. For example, primarily at very small length scale, that means very minute scale, microscopic scale, in micrometers or nanometers, okay, in angstrom, in Fermi, or 10 to the negative 15 meter, for which classical physics simply offer no explanation. Classical physics, or sometimes we call it Newtonian mechanics. That means the formulas of Newton, which we study in lower level courses, is usually for macroscopic situation. That means big compared to an atom. Big things such as ball, car, our body, moon, star. Okay. At very small scale, such as inside an atom or a nucleus, then basically classical physics offers no explanation. How to explain particles inside a nucleus or inside an atom? Classical physics cannot explain it. So, basically, quantum theory or quantum physics ultimately prevail because it agreed with experiments. Okay. So quantum mechanics is so counterintuitive and strange in many predictions. In each of the experiments below, physicists has developed a classical theory in these three. For example, black body radiation, photoelectric effect, Compton effect. Okay. Physicists has developed classical theory for those experiment or those physical effect which fail to account correctly the experiment. We get experimental result, then try to explain the phenomena by using classical physics in black body radiation, in photoelectric effect, in Compton effect. But our classical theory cannot explain correctly. That means we fail to explain black body radiation, photoelectric effect, Compton effect, by using classical theory. Later we'll discuss a little bit on this and why we need to study quantum mechanics. Okay. For example, now let us go to black body radiation. I think you have come across this in your lower level, such as in thermodynamics. Okay. Okay. Black body radiation basically come from a black body. A black body need not be necessarily black. In this diagram, for example, we have a sphere, for example, a hollow sphere with a small hole here. This is a small hole. And if you shine a radiation inside it, maybe heat or maybe light, okay, then it will be reflected inside the sphere, okay. And of course, if you want it to be a good absorbent, you blacken the surface of the inner surface of the sphere. Then basically at each reflection, you can see that the intensity of the light decreases. Okay. So after some time, you can see that the intensity of the light decreases further until it almost vanishes. And the probability of the light to be re-emitted, that means to go out from the hole here, is very small, because you can see that the reflection is at an angle. Then you can see that multiple reflection occurs inside the sphere, and the probability of the light to be emitted back is very small, almost nil. So even though if you shine a light into the hole, you can see that the hole is completely black because no light is emitted. At the same time, if the cavity here is heated, that means at a temperature, as you can see, for example, in your kitchen, if you heat something, for example, iron, after some time it will glow, okay, become red, then yellowish, and so on and so forth, okay. That means it emits radiation, okay. It emits radiation. But for a cavity like this with a small hole, if you heat it, even though all the surface of the cavity here will glow, but the brightest spot will be from the hole itself, because you can see that the inside of the sphere here will be heated and glow, and where high intensity of radiation will be coming out from the hole. That's why usually black body can be defined as a good emitter and good absorber. If you shine a light, it's a good absorber, but if you heat it, then it is a good emitter. And emits radiation in spectrum. We call it what? At all wavelengths. We can say that, but actually it is a curve, okay? And Stefan and Boltzmann have studied the power, total power given off by the black body radiation equal to sigma A T to the power of 4. T is the temperature, or since this sigma A is constant, the power is directly proportional to T to the power of 4. That means to the temperature, okay? It is more or less like this. If you want to convert it, total energy density rho. Total energy density is equal to 4 over C, where C is the speed of light, multiplied by P over A, where P is the power, okay? And the most important thing, power is directly proportional to T to the power of 4, and the same thing with total energy density rho is directly proportional to the temperature to the power of 4. And this is the curve, or the spectrum of black body radiation. You can see here that it has a high peak here, okay? I just put two diagram here because in some books use wavelength as the x-axis and some books use frequency as the x-axis. Okay. The relationship between frequency and wavelength is given by nu equal to c. C is the speed of light divided by lambda. Okay. Okay. Usually at lower physics courses, most textbooks use wavelength because in the old days when the black body radiation was studied, it was based on the wavelength. That means the scientists during that time study wavelength of the radiation or light given out by black body radiation. And when Max Planck proposed his quantum theory, he used frequency. That's why in later or modern physics or in higher level physics books, sometimes most of the time they use frequency here. As you increase the temperature here, for example, 1000 Kelvin, here 1500 Kelvin. As you increase your temperature, there is increase in temperature. Of course, the area under the curve also increases. Okay. Apart from that, you can see that the peak shifted to the right. That means to higher frequency. Or in case of the x-axis being wavelength, you can see that as the temperature increases, the wavelength decreases. So you can see that now frequency is inversely proportional to wavelength. Okay, that's one thing. And this shift is called the Wind displacement law. That means if it is in frequency of the peak is directly proportional to T. That means if you increase T, the frequency increases, or inversely proportional to lambda or wavelength. That means if you increase T, then lambda decreases. This is the first feature is on the amplitude. That means the height, and you can see here that it is actually Stefan Boltzmann law. The rho here is equal to a t to the power of 4. That means rho proportional to t to the power of 4. This is just the area under the curve. Okay. So the spectrum here tell us two major features. One is the area under the curve, which was studied by Stefan Boltzmann. Then the shift of the peak, which was studied by Wiens. Okay. So 19th century physics had a theory to explain the theory failed to produce the observed spectrum. Okay, during that time they used thermodynamics basically to determine the energy. Energy is directly proportional to temperature T. Okay, where K is the Boltzmann constant. Okay. Then this is classical physics. Okay, in classical physics, energy is equal or directly proportional to temperature, and Rayleigh engine use this classical physics concept and produce the Rayleigh-Jean formula. This is the Rayleigh-Jean formula. So this is the energy density. Okay, equal to 8 pi kT per c cube nu squared. But it does not work. It does not work means that it was not successful in explaining the results from experiments. Okay. So what Rayleigh-Jean got using classical physics principle is this, that the dash curve here is a Rayleigh-Jean curve. Okay, if the x-axis in wavelength, then the Rayleigh-Jean curve is this, the solid line here. In frequency, you can see that it fits only at low frequency. That means the curve here is the experiment from experiment. Rayleigh Jean formula only fit at low frequency. At higher frequency, basically, it fails to explain the. In fact, several scientists, apart from Rayleigh Jean, who studied this black body spectrum and proposes formulas and so on and so forth, but they fail to explain it because they use this classical physics relationship. Okay, and this energy equal to kT is correct in thermodynamics, in other physics, classical physics topics. Okay? For example, in thermodynamics, okay, it's correct. It's not wrong, but it cannot explain black body radiation. Okay. Then Planck proposed his hypothesis. Planck's idea was to modify the theory to make the mean energy of the particle as a function of frequency. This contradicts the classical physics concept. Okay. In classical physics, E equal to kT, but now he proposes E is directly proportional to frequency. Now he proposes E is directly proportional to frequency. In classical physics, E is directly proportional to temperature. Okay. Then he also suggested that the energy given out by the black body radiation cannot take any arbitrary values of energy, but only discrete multiples of some fundamental energy. Okay, and this is what Planck proposed. That means now your energy cannot have any arbitrary energy, but it can only have zero energy, h nu, 2h nu, 3h nu. That means discrete values, and this is what we call as quanta. That means classically the radiation energy is supposed to be electromagnetic wave, continuous electromagnetic wave like that. But now it seems that your energy is discrete. That means localized, some sort of like wave packet. You have this wave packet. Inside that you have the wave function. Okay. Each wave packet have energy E equal to h nu. This one also energy E. This one also energy E. That means now the energy given out by black body radiation is not continuous anymore. It is like in parcels of energy or packets of energy. Each packet have energy E equal to h nu or 2h nu or something like that. That means certain discrete values. This is how the word quantum comes from. Basically, it's from quanta. That means discrete values. And by using this, Max Planck proposed the energy density formula. Okay, you can see that the energy density formula here is only slightly different, or a little bit different from Rayleigh Jean, in the sense that it has -1 here from this derivation. Okay, and why Planck's hypothesis was accepted? Because, as you can see here, Planck function fits the observed data perfectly. Okay, you can see here that Planck wave function, the solid line is the wave function, and the dots are the experimental values, and it fits perfectly between his calculation and experimental or observed data. Okay, so even though we might ask, how can Planck suddenly suggest something which is drastic or out of the blues? In thermodynamics, E equal to kT. Now he suggested that the energy of the radiation, first one is that it is proportional to the frequency rather than temperature. The second one, that the energy is discrete or in quanta, not continuous anymore. So people ask, how can you propose this? But when they see the result, Mark Planck calculation and explain the result, it fits perfectly, so the scientists have to accept. Even though we cannot say that it is a law yet, it is still hypothesis even now. But people cannot reject it because he managed to explain black body radiation. Okay. Now, the idea of Planck is that radiation energy is in packets or in quanta, and each quanta have energy E. Cannot have any arbitrary energy, but E must be proportional to frequency rather than temperature. So people or scientists at that time have to work vigorously. What is this relationship between Planck's blackbody spectrum or his hypothesis, the two hypotheses, E proportional to frequency nu, and also the energy are not continuous but in quanta. What was his hypothesis relation with classical physics? Because we cannot reject classical physics because it works in ordinary life, in macro scale, in large scale things like our body, cars, ball, marbles, and so on and so forth. So is there any relationship? So they try to find the classical limit of Planck's blackbody radiation. So they start with Planck formula, energy density formula. Then we assume h nu is less than kT, or h nu per kT much less than 1. H nu is the energy at the photon, okay, and kT of course the energy in classical physics, and they can derive Rayleigh-Jean formula. They can derive Rayleigh-Jean formula by using Max Planck formula. Okay? So there is a relationship between Rayleigh-Jean formula and Max Planck formula. And remember that the relationship is when h nu is small compared to kT. That means at small frequency. And it's shown in the graph just now. At small frequency here, Max Planck formula, which fit the whole spectrum here, is equal to the Rayleigh-Jean formula. So this is what we call classical limit. That means Max Planck formula, if you consider at classical limit, it is equal to the classical formula of Rayleigh-Jean. That's one. Okay. That means now there is a relationship between Max Planck formula with the Rayleigh-Jean formula. Okay. Now, people try to derive Stefan Boltzmann law from Max Planck formula. They start again with Max Planck formula. Then they do some substitution, h nu over kT again, and so on and so forth. They get this relationship. And this relationship is similar to the Stefan Boltzmann formula. Stefan Boltzmann says that the energy density is directly proportional to the T to the power of 4. This is Stefan Boltzmann. And from Max Planck formula, basically we can derive that. You can see here the terms which I rounded it is basically a constant. So rho is directly proportional to temperature to the power of 4. So now you can see that by proposing his hypothesis, Max Planck managed to explain black body radiation. And then not only that, basically his formula can be used to derive Stefan Boltzmann law and also Rayleigh-Jean formula. And now Wien's law. Wien's law says that With increased temperature, then the frequency of the peak increases. So derivation of Wien's law, blah, 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 and so on and so forth. Now, again, we can get Wien's displacement law where frequency is directly proportional to temperature. These are constants, okay? So again, from Mach-Planck formula, we can derive Wien's displacement law. So you can see from here, basically, scientists cannot what? Cannot reject Mach-Planck's hypothesis. We have to accept that because it can manage to explain the spectrum of black body radiation, and from Mach-Planck formula you can derive all the classical formulas. Okay. The second phenomenon which make people have to accept quantum physics is that this photoelectric effect, and this was explained by Albert Einstein, and because of photoelectric effect, Albert Einstein got his Nobel Prize. Okay, this is the experiment. You can see that if you have metal, then you shine light on it with an energy h nu, E equal to h nu. Then you have electron coming out from the metal, okay, negative charge. And by using classical physics, scientists could not explain why by shining a light, which is supposed to be wave, just electromagnetic wave, and an electron is ejected. Until Einstein comes along, then he proposed that the energy of the incoming photon according to Mach-Planck hypothesis. That means E equal to h nu rather than E equal to kT. And by using the idea of Mach-Planck, Einstein managed to explain photoelectric effect. That's why in photoelectric effect, the Mach-Planck constant H appears too. So you have black body radiation and photoelectric effect with H there. It suggests that it has fundamental significance. That means Planck constant now is almost everywhere. The third phenomenon which strengthens or basically it proves that Mach-Planck hypothesis have to be accepted is the Compton effect. What happened in Compton effect? You have an electron here, then you have incoming photon, that means electromagnetic radiation. This photon managed to interact with the electron and displace the electron. That means the electron is moved or recoiled with a new momentum PE and energy EE. And that means the incoming photon is like a particle. It's not a wave. Okay? That means we can imagine it is packets or bundles of waves with electromagnetic waves inside it with energy EI here. Okay? Because we know that in classical physics, if we have a marble, in order to move a marble, we need another marble. That means another entity with a mass or an energy. Here we have an electron which has mass m, while electromagnetic wave, it has no mass, but still it managed to displace the electron. So again, the concept of the photon coming here is based on continuous Mach-Planck hypothesis, and he managed to explain that using the conservation of energy of momentum. Okay, blah 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 here, derivation and so on and so forth. I think you need to read on your own. Now, because of this, now we have two ideas about light. Is light a wave or a particle? Okay. In classical physics, light is considered as continuous sinusoidal wave, while in quantum physics, it is more like a particle. That means now we have packets of waves with energy E. Okay. Now we have this light. In classical physics, in order to explain phenomenon of reflection, refraction, diffraction, young double slit experiment, you have to use wave properties. Remember that we use Huygens wavefront principles. Okay. But in quantum physics, to explain black body radiation, photoelectric effect, Compton effect, you need to use particle properties based on Planck hypothesis. Okay? Both are correct. If you want to explain reflection or refraction of light, for example, you use particle properties of Planck hypothesis, you cannot explain it. You need to use wave properties. The same thing, if you want to explain black body radiation, photoelectric effect, if you use wave properties, you cannot explain it. You need to use particle properties. Now, light have two properties, wave and particle properties. This is what we call as wave-particle duality. That means light, at certain experiment, we need to use wave properties to explain the phenomenon. In another experiment, we need to use particle properties to explain the phenomenon. Okay. Now, light might behave like a wave or particle depending on what experiment you are carrying out. Okay. Then another question arises: if light, which in classical physics is considered as continuous wave, and later in quantum physics it has particle properties, what about another way around? That means matter. Matter consists of particles such as atom, molecule, and so on and so forth. Of course, they have particle properties because matter, such as you and me, consists of particles, atoms, molecules inside our body. Okay? If light, which was previously considered as wave, have particle properties, what about particle? Can it has wave properties? This was made out by Louis de Broglie by making a proposal. Matter which is composed of particles might also behave like a wave. He proposed if light can also act like a particle, so particle can be like a light. Also, before this slide, wave particle duality says that light can have particle and light wave properties. Why not particle? Particle can also have particle properties and wave properties. And de Broglie suggested a wavelength of lambda equal to h over p. Again, you can see h is there. That means he based his idea on Max Planck ideas too. And in the example there, you can see that why we cannot see de Broglie wave for a 70 kilogram human being walking at 1 meter per second. While in the second example there, what about electron? So basically you can see or we can observe electron, de Broglie wavelength, and so on and so forth. So all the argument are in the lecture note. Please go through. I think time is not enough. So if you have any questions, just email me. Thank you very much for your attention.